So good afternoon, everyone. As a part of our Azadi Ka Amrit Mahotsav celebration at Aries, we are happy to have Dr. Bhargav Vaidya in our weekly seminar today. So Bhargav did his PhD from Max Planck Institute of Astronomy at Heidelberg in Germany in 2011. And then he did a few years of postdoc, first at University of Leeds in UK, and then followed by University of Torino, Italy. So from 2017, he is an assistant professor at IIT Indore, and where he is currently now. So welcome, Bhargav. And
thanks.
Yeah, so you can share your presentation and you can go ahead.
Okay. Can you see the presentation full screen?
Yes.
Okay, great. And can you also see my cursor?
Yes.
Okay, great. So let me put this near the bottom. Okay, right. So good afternoon, everyone, and thank you first of all to Aries for inviting me for this talk in the weekly seminar. And I would like to today discuss about some of the recent results which our group has obtained, understanding the interplay of various physical processes in AGN Jets using numerical simulations. As far as in particular, I'll be focusing on some of the recent work that have been published with help of my master student, Kilo-parsec, who is also now a PhD student at University of Purdue. And a couple of my PhD student, Shri Acharya, and also a postdoc in my group, Indore, Dingya Kalpa. And this is basically a group which is supported by the Max Planck Partner Group. And of course, I have other collaborators working in the Pluto Code Working Group and the Panjan Mukherjee, who is at Ayuka. So what I'm going to talk about is basically give you an overview of how AGN Jets are and what is basically the physical processes that are involved in AGN Jets, and give you an idea of what are the problems that we are tackling and why such problems have to be tackled using numerical simulations, and what sort of cutting edge numerical simulations which have been doing in this community of AGN Jets modeling. So if you look at the history, if you go slightly into the history of AGN Jets, it's not a very recent history, it's about 100 years old now. On the left, you basically have an image taken in an optical band of Active Galactic, where you can basically see this little curious ray of light, which was suggested to as a first indication of some tail-like structure that is appearing. People at that time in 1918 didn't know actually that these are essentially relativistic jets that are actually powered by the central black hole. But since 100 years, there has been a significant amount of progress in understanding these structures, these elongated structures in multi-bands. And one of them, classic example, is a blazar source, which is 33273. This is here, which has been observed with VLA, and this has been shown here that these curious ray of light basically have much more complex structures which are filled with knots and can be wiggly as well in shape. Now, if you go to the much more recent history, now people have used this consortium of sub-millimeter telescopes, which is essentially called the Event Horizon Telescope, and they are able to now really image the vicinity of the black hole or the singularity that is existing at the center of the M87 galaxy. And here you can basically see this feature that is a famous image of the M87 black hole, where you can see the light coming from the sub-millimeter band. And very, very recently, using ALMA, they have been able to now also kind of penetrate into the polarization signatures, where you can see that the structure of the magnetic fields is kind of colloidal in nature. And this kind of indicates that since 100 years, there have been significant progress from the observational perspective to really understand what is really happening at the central engine where the jets are essentially launched. These AGN jets are essentially nothing but fast and collimated beam of plasma that are kind of released from this central massive black hole. So the question now is that why really you want to study such kind of structures which we have been studying since, or at least observed since last 100 years. Now, of course, there are several new concepts or new ideas that have come up when it comes to AGN Jets. And one of the basic and one of the most important aspects of AGN Jets is that these jets have been excellent test bed, excellent laboratory to basically study multi-messenger astronomy. And the multi-messenger astronomy has propelled since last few years or so, where people have now started to really detect neutrinos, high energy neutrinos using the ice cube experiments and so on and so forth. And one of the signatures or one of the important aspects of these neutrino emission is mainly associated with a blazar source which is over there, and therefore these AGN jets are believed to be an important contributions towards multi-messenger astronomy. Along with the multi-messenger aspect, we all know that AGN jets have a multi-band emission process, where you basically can see on the top a structure that is of M87 at very different scales, where you can basically see the 90 centimeter VLA, where you can see a much larger galaxy structure. And then if you go on much closer and deeper, you can see how the jet is kind of getting evolved and emitted from the central black hole. And if you go much more closer and closer and more deeper and deeper into the central part of the black hole, you can see how the jet is kind of emitted out in some sort of a jet spine and sheet structure. That is what we call technically, but this is essentially like an onion shaped structure where you have a hollow structure in the between and a much more turbulent beam-like filamentary structures on the side. So such kind of jet features are now also observed very recently in Centaurus A as well, along with M87. And in addition to that, as I mentioned, that you have a combination of both X-ray emission, which is very high energy emission, as well as radio emission that is mainly coming from the jet itself. And most of this emission is kind of attributed to the non-thermal processes that actually happen in these jets, and mainly synchrotron emission that is actually present in these kind of structures. Now, when you talk about synchrotron emissions, of course, one comes to a picture that, okay, these jets are highly magnetized in nature. Now, if you look at the magnetic fields in general, and you do some simple back of the envelope calculations of how much energy or how much time will it require for electrons and protons inside these jets to basically cool down in presence of the magnetic fields that are existing in these jets, then one comes up with a timescale which is far, far shorter than the typical timescales of these AGN jets. And therefore, one ideally should not expect any emission from such kind of AGN jets at very, very large scale. But despite of this simple calculations, we do see emissions extending up to kilo-parsec and megaparsec scales due to synchrotron process. And therefore, one comes to a conclusion that there must be some sort of an in situ acceleration processes that must be happening within these jets, which can accelerate these particles to higher energy, and then they are cooled down by the synchrotron and other Compton processes that can happen. So here is some sort of a cartoon picture of the Cygnus A in the background, where you can see the radio image. And on top of that, I've basically just indicated to you the different physical processes that are actually acting in tandem in these regions. I've just shown them in representative structures, but they can act in tandem together. So definitely in regions where you have extremely strong magnetic fields, you have particle acceleration mainly governed by the process of magnetic reconnection. There have been models by the group in Purdue and so on to explain extremely fast flaring activities using these magnetic reconnection processes. If you go to much larger scales on the lobes and where you have much weaker magnetic fields, there the primary acceleration mechanisms that is mostly attributed is to shocks and turbulence and so on and so forth, where you can basically have both shocks and turbulence acting together and accelerating particles continuously as they are getting cooled due to synchrotron process and emitting radiation. In addition to this confluence of acceleration processes, of course, these jets are highly relativistic in nature, And this has been discovered because of the fact that you always see a jet to be one-sided, that is, only one side of the jet is getting brighter, and that is mainly because of the relativistic effects where and because of the beaming, that the other part of the jet basically is not beamed towards you and therefore not enhanced emissionally, whereas the part of the jet that is facing towards you is relativistically beamed and enhanced on that particular direction. So if you look at this whole jet, this whole jet covers a scale of about 1 megaparsec in size. But all these processes that you are dealing with, where you basically have an interplay of all these physical processes that governs the overall structure and the overall mechanism, the radiation mechanism, happens at a much more microphysical scale. And therefore, one cannot really handle this kind of a problem and very simply analytically. And therefore, one requires a much more complex understanding where you have a complex interplay, and thereby you require some sort of help from numerical simulations. If I actually have to draw a cartoon picture representing AGN jets, and essentially to represent the multi-scale nature of these AGN jets, here what I will do is I will divide these AGN jets into different zones and then discuss each of these zones during the part of my talk and understand what are the properties of AGN jets in each of these different zones. So the classic way to distinguish these AGN jets are into 4 zones. The first zone is the launching zone, where you basically have the jets pretty close to the black hole, and the jets are extremely strongly magnetized over there. They have a much more larger opening angle. You have a much more turbulent mass loading effects. And of course, there is this connection between the disk and the jet, which is still very elusive, and we really do not understand the real launching process between the underlying accretion disk and the jet itself. So this is the launching phase where we will come, and this is only the sub-parsec phase of the AGN jets. If you go slightly above, where you have the more narrow-line regions and so on, where you basically are up to few hundreds of parsec in size, there you have much more dynamical processes that are going on along with strong magnetic fields. And because of this dynamical process and strong magnetic fields, these jets are prone to emit the instabilities. And you have processes going like magnetic reconnections, collimated shocks that come into picture over here. And these are essentially the processes that happen during in these parsec and sub-parsec scales, and that mainly governs the dynamics of these jets. Up to these scales, these jets are extremely magnetically dominated. And the moment you go to much higher, like more than 100 or kilo-parsec scales, they become kinetically dominated. And essentially, the dynamics is governed by the kinematics or the thermal pressure and so on, and not rather by the magnetic fields. And at this particular stage, you are prone to all sorts of shock acceleration, turbulent acceleration, kink instabilities, and sausage instabilities, as we will see. And this is mainly the reason where you have strong amount of synchrotron emission that is coming at much larger scales and fairly detected by several radio telescopes. And if you look at another aspect of AGN jets is mainly the dissipation scale, where you essentially deposit all the amount of energy right from the central black hole up to very, very large megaparsec scales and affect even the cluster scales in this particular region. So the focus will be on these first initial 3 zones, and I will discuss in detail some of the aspects that we have addressed through numerical simulations, understanding these problems. So let us start by zooming really in very close to the black hole. And if you see basically on the top, I have the main questions that you need to ask when you want to understand what is happening really close to the black hole is, question 1 is, how are these jets launched? We really don't know this yet. What is the interplay of, there are different kinds of jets as we will discuss. The Blanford-Snag jet, which mainly is the fast moving jet that comes from the central black hole, and the Blanford-Payne jet, which is the slow moving wind that comes into picture. And how important is the underlying accretion disk or the properties of these accretion disks that govern these flows? Now on the top, you basically see the radio image of the VLA, where you see this knotty structure. So the question is that what properties of the disk and the disk jet connection gives rise to such knotty features at larger scale? Even this is an interesting work recently by Brisson et al. Using Mojave dataset, where they actually say that this M87 jet has much more filamentary jet-like feature that is coming out with this hollow. And to understand why such kind of jets can come out of turbulent mass loading, you have to really understand from the perspective of numerical simulations. If you look at this image over here, this is a jet radius versus projected jet length. And you can see from different telescopes, people have probed really close to the black hole and have understood that these jets, when they are launched pretty close to the black hole, have a much more parabolic shape structure to begin with, and then they essentially go up to z as proportional to r squared. So it's more like a parabolic. Initially, it's r to the power 1.6, and then it becomes z as proportional to r. So it becomes parabolic beyond the Bondi radius. So it all starts with a much wider base and then becomes much more collimated as you go further and further beyond this thing. So really, to understand this, there has been, of course, theoretically, there have been several models that have been proposed and to understand the launching of these jets. And the two classical models that have always been discussed by the same author is Roger Blandford. The first one is the Blandford-Snag jet, where essentially the material from the disk is basically dragged because of these electric forces that are produced because of the rotation of the black hole. And you tend to basically throw this very light matter along the toroidal magnetic field lines with extremely high speeds and relativistic speeds to go up to very high relativistic speeds. And this is mainly happening pretty close to the black hole. But the other counterpart is mainly the Blandford-Payne jet, which is, or the Blandford-Payne disk winch, where you essentially have the magnetic, where you essentially have the material from the accretion disk being dragged or being attached to these magnetic fields like these beads on the wire, and where they are magnetically dominated. And as these plasma flows move along the magnetic field lines, they actually dominate later on. And right from a magnetically dominated region, you become a kinetically dominated region because of this thing. And they bend the particular magnetic field lines, toroidal magnetic field lines, to produce toroidal magnetic fields. They're essentially responsible for channeling and collimating these particular flows. So these are typical textbook models which has been proposed to explain such kind of AGN jet launching. So the question is, do we actually see them in simulation? So here are some recent simulations which have been demonstrated using the state-of-the-art GRMHD codes. So GRMHD codes are essentially general relativistic magnetohydrodynamic codes. They are fairly well advanced stage now in the community. And what people do is they essentially solve the set of Maxwell's equations and the fluid equations in the GR context. And here is such an example where I have shown a structure of the density, disk density. This is basically the black hole, and this is basically a disk, where you can see that the disk is kind of getting, it creates a much more chaotic environment where you have the disk either getting detached from the black hole, and you have the wind, and the white field lines are essentially the magnetic field lines, where you can also have these wind-like structures. But mainly this is the Blandford-Snag jet, and this is more like a Blandford-Payne, but mainly governed by the toroidal component of the magnetic field. These are not classical Blandford-Payne kind of features. People have also studied in three-dimensional calculations where they do a tilted accretion disk, where people have seen, especially Matt Liska and all, you can see some sort of wiggling structure in your jets because of the tilted accretion disk structures. But this is mainly focusing on the Blandford-Snag jet in general. But up till now, no simulations have shown existence of classical Blandford-Payne disk winch in using GRMHD simulations. And that is one of the main motivations of our study that we carried out very recently with Indore, and where we started with a very simple initial condition using a GRMHD code called Bhargav. And we started with a thin accretion disk, which is rotating, and following the Novikov-Kohn approach, which is essentially a stable accretion disk under this GR formulation. And we incorporated a pressure balance, a vertical pressure balance, so that the disk doesn't fly off with radiation pressure. And we incorporated certain magnetic fields inside this with different inclinations to begin with. So these are toroidal magnetic fields you can give So the inclination is governed by this parameter m, which states that if m is smaller, you have a much wider inclined thing closer to the disk. But if m is larger, then you have much more vertical magnetic field structure. So we start with these simple configuration and we try to understand what really happens to such kind of disk. So I can just quickly demonstrate a movie. Just let me know if you can see the movie. So let me play this movie. So here is basically the disk density profile, and the lines are essentially the sigma equal to 1. So that basically indicates highly magnetized features. So here you basically can see very highly magnetized jet-like structure that is coming out. But on the outer part, you have much more turbulent wind-like structure. This is mainly the Blandford-Payne wind, but highly turbulent, governed by the accumulation of the toroidal magnetic flux, which are basically getting accumulated here. But at the outer stage, you basically see much more smoother Blandford-Payne-like wind, as we will see. And this is exactly what is happening. But what is another interesting feature that we observe, if I play this movie again, is that this disk detaches from the black hole and comes back again. So this kind of oscillation behavior is also seen in such kind of disk. And this is extremely important from the perspective of variability explanation and explanation of variability at much shorter scale. So here you can see how the disk is basically getting detached from the central black hole, and then again getting accreted back inwards, and so on and so forth. So this is, yeah, it's getting detached and again getting accreted, and so on. So it basically keeps on continuing like this, and you basically have a much more wider picture. And if you look at this particular structure in the vertical velocity, which I've shown here in red and blue, the red is like positive going upwards in terms of C. You can see that this inner part is highly dark red in color, where you basically have a very strong wind, the strong jet, that is the Blandford-Snag jet, which is mainly connected to the ergosphere, where you have the polarized field lines connected to the ergosphere, indicating this is a particular Blandford-Snag jet. So if you look at slightly more, this is a slightly more busy plot. Here you can see that there is a thin disk. You can basically divide it into 3 different regions. You have a thin disk, which is highly dense. You have a disk wind, which is slower, typical velocities of the order of 0.1 to 0.2 C. And then you have a funnel where you have strong polarity magnetic fields and very fast jets, mainly the Blandford-Snag jet, and it's also highly magnetized. And it is moving with a Lorentz factor of about 10 or so, maximum Lorentz factor of the order of 10. And if you look at the toroidal component of the magnetic field, here you can see the black line, where essentially what we call the magnetic surface, so alphanic surface, where you actually have this structure, the wind basically starting subalphanically, so less than alphan speed. But as you cross this surface, it becomes super alphanic. So initially it starts with magnetically dominated, and as you go above, it becomes kinetically dominated, indicating that you are starting to see the evolution of a Blandford-Payne kind of disk winds for the first time in any GRMAG simulations, along with the toroidal, the turbulent component of the magnetic wind and the Blandford-Snag jet that is present. And if you basically compute all these mass flux and the wind rates and so on, you can clearly see that for example, for the case that you have considered, which we call the MAD case, or the magnetically arrested disk case, which is highly magnetized, what really happens is that the flow, basically the magnetic flux gets accumulated at the center, and it breaks the symmetry and keeps on doing oscillations due to reconnection, and you basically have these oscillating features, even translated into your wind rates, into your outflow rates and jet rates. And that is essentially responsible for this naughty kind of features that we also see in our calculations, in our simulations. Going further, we also observe that these toroidal component magnetic field, which is present over there because of the rotation and the accumulation of the magnetic flux, tends to get adversed away from the disk, forming these reconnection plasmoids. So this is a concept of magnetic reconnection, which also happens, by the way, even in the solar surface, in the flares. The same thing happens even very close to the black holes, where you can basically see these reconnection zones and these plasmoids which are actually being formed. And these reconnection sites can be extremely important for acceleration of particles, even in these extremely close by regions pretty close to the black holes. And they can be very much responsible for producing hadronic emission, and therefore even neutrino emission can come out. Very high energy neutrino emission can come out from such processes. However, these are just 2D simulations. We do see that there have been recent progress, and people have been doing 3D simulations where you also see such kind of plasmoid features being developed even in 3D simulations, where you have a strong, so basically in 3D they are called as flux tubes or plasma tubes, where you actually can generate these strong flux tubes of matter which can accrete and also accelerate particles. So in general, from our model, we have a much more toy model, a much more updated toy model from our jet launching feature. That, of course, it's not a standard Blandford-Snack or Blandford-Payne, but essentially it's a combination of both, where we actually suggest that you have a very thin accretion disk, high density accretion disk at the center, followed by a Blandford-Payne disk winds, which are slower, typically of the order of 0.1 to 0.2 C, followed by a shell of a turbulent toroidal magnetic field dominated. So this is D5 dominated wind. And then in the center, you basically have a Blandford-Snack jet, which is extremely fast and moving with almost relativistic speed. So, and in these turbulent components, you basically also see plasmoids being formed. This is a general picture that we actually put forward from our study of launching at the center part. And going further, that is going slightly above and the higher phase, let's go into the parsec scale. We actually see that the mostly important aspects of studying at the parsec scale are something what we understand from the variability of the blazars. The blazars are essentially AGN Jets in which you have a very preferred line of sight where you can actually go and look through the jet and see what is really happening at the inner part of the jet. And the aim of this exercise is that really you need to understand what is the features or what are the physical properties that are responsible for variability. And as you are, typically the variability time scale can range from few seconds or few minutes or intraday variability, and it can range up to, let's say, few long-term, let's say, within few years or so. So which physical processes are responsible for such variability signatures at shorter time scales and longer time scales is something that we need to understand. And also certain blazars show wavelength correlation between optical and gamma, while others do not. So what are the physical processes that can govern such kind of wavelength correlation is an important question that needs to be asked. So here on the left is a very recent paper by one of my colleagues here in IIT Indore, Amit Shukla, who has shown from 3273, I think 3273, that you can have very high, very short time variability within this gamma band using the Fermi data analysis. And such kind of short-term variability is a challenge for us to explain. And one of the important ingredients to explain this could be magnetic reconnection. But what is our interest is to understand much larger scale, that is the long-term variability. And one of the important or one of the models that has been proposed that has been utilized to understand the variability on CPA 102 at a much larger scale is what we call the geometric model, where essentially the idea is that the jet has a kink-like structure. And if you look at a different viewing angle, this kink-like structure can have much more relativistic boosting effects towards your line of sight, and you basically can get long-term variability on time scales of years. So in order to understand that, of course, when you look at such simulations or when you look at these jets at parsec scales, we are well aware that these jets are prone to MHD instabilities, where you can have several types of instability. So here is an example of the instabilities that are typically existing in these jets. So on this case, I've shown here is a sausage instability, which is thought to be one of the important mechanisms of producing these knots, where your toroidal magnetic field kind of pinches jets at a particular region. Or you can have a kink-like instability, where you basically can shake the plasma column or the jet plasma, and basically it forms like an S-shaped kink structures. But also important in these fields is basically the instability that is generated due to velocity shear, and that is essentially called the Kh instability. So these kind of instabilities are working in tandem, and they also actually work in unison. And therefore, a non-linear interaction between such instabilities is possible. And one needs to understand that to really understand what is really happening. So what we do is, this is a work done by my PhD student, and we have this has been published very recently. So what we do is we actually capture certain small portion of the jet, very close or focusing on the parsec scale region of this particular jet here, or some particular jet, and we model this particular plasma column with an initial toroidal component or helical component of the magnetic field, and highly magnetized, because these regions are highly magnetized in nature. And what we do is we study the evolution of this particular plasma column to understand what really happened. So here is a time evolution of such a plasma column, where we have perturbed this plasma column with a kink-like perturbation, and you can see how the jet is kind of getting disturbed, and the initial helical magnetic field is getting from an initial helical distribution to a much more chaotic distribution. And on the background, you can basically see the density structures, how it's basically getting turbulent, and also and basically what happens is that the highly magnetized structures become dissipated and reduced in magnetic field strength. And this is an important aspect, because after this stage, the magnetically dominated jet becomes kinetically dominated, and therefore there must be some channel to dissipate such magnetic energy. And this is exactly what we show here when we basically take such a plasma column and we make an energy estimate with different models that we have done here, where N1, N2, N3, and N8 are different perturbation modes that we have incorporated into this. And what we definitely see is that you have a much more linear phase to begin with. The linear phase, this is the kinetic energy in one particular slice of the plasma column with time, and this is the magnetic energy in that slice itself. So you can see that how the initial magnetic energy kind of dissipates because of these instabilities that are produced. And these are laser jets, a typical Lorentz factor of 5 have been incorporated in magnetization of 10. And initially you go from a linear phase to a non-linear phase, where you basically see this transition from the initial disturbance to a much more complex turbulent dissipation. So this is essentially how the energy evolves. But the important aspect, so this is from the dynamical perspective, but the important aspect that we observe is from the observational perspective, is really to understand how do you get the emissions coming out of this. So for this particular case, when we do one zone modeling, there are several aspects of studying emission from lasers, and people have been doing one zone modeling to fit the SEDs. There are several pros of such model. It is extremely simple, and one can incorporate very highly complicated emission mechanisms into this, can be parameterized and can be studied. However, the disadvantages is that it's a slightly steady state approach, and there are several parameters to actually play with, and there can be rising to degeneracy associated with such kind of fitting of SEDs. So what we instead do is we rather develop some sort of a multi-zone modeling approach, where we post-process our three-dimensional simulations with basically fixed spectral information and produce synthetic light curves and SEDs. There are of course less free parameters to deal with. However, the disadvantage is that with the fixed spectra, you do not incorporate cooling and acceleration physics into account. But nevertheless, when you look at these structures, we can definitely see how these kink instabilities can produce some periodic emission features that you can see here. So this is basically the emissivity that is observed over some scale emissivity. And this is the Doppler factor, where you can clearly see that how certain portion of the jet, which is pointed towards you, is kind of getting brighter because of this helical structure. And one can try to see if such features can help to understand the variability. And that is exactly what we have done here, where you can see the line of sight structure of this particular jet, where you can see, and we have focused on one particular aspect, one particular region of this particular jet when you integrate along the line of sight, and you can see how this SED or the flux in this particular region over time varies with time. And this is mainly because of the fact that certain portion of the kink will come towards your line of sight, and you will basically see those features getting more brighter because of the relativistic effect. And thereby you can actually also then do all sorts of estimates based on period and so on, and find out what is the velocity of such kind of things, and all these studies. But this was only focusing on one particular region. If you focus on the whole column itself, you can also get to see some sort of variability signatures that are coming from such scales. So this is basically, if you see the x-axis, it's covering almost about 20 years in time frame. And with such kind of studies with two different viewing angles, you can find typical fractional variability in the optical band. This is mainly in the R band that we study synthetic emission. In the R band, you can see typical fractional variability of about 30% or so. So this is fairly consistent with observations. And if you then try to see some additional observational features, which we do, this is called the relative variability amplitude. This is something which observers tend to estimate from the light curve that they get. And then on the x-axis, you basically have a dynamical feature, which is the dissipation rate or the growth rate. You can see there is a one-to-one correlation between the relative variability amplitude and the growth rate of this kink instability. This suggests that these kink instabilities definitely have some signatures or some influence in determining the variability at much larger scales, especially to explain these long-term geometric variability signatures. And now, finally, going into the largest scales, where we go into the much more higher kilo-parsec scale, where you have all sorts of shock features, and there becomes much more important. You tend to ask these questions that, okay, now that your energy is dissipated, how do we have shocks coming into play? How do these MSD-driven instabilities survive these jets? And how do these instabilities impact on the non-thermal emission on a much more continuum non-thermal emission that you have? So of course, there have been simulations here. You can see this classic picture of deceleration of these jets, especially FR1 jets. The FR1 jets decelerate as you go much further into kilo-parsec scale. So even though when we started with a gamma 10 and gamma 5 in the sub-parsec scales, when you reach at very large kilo-parsec scales, the jets tend to become mildly relativistic, or at least non-relativistic in nature. And the ambient medium has significant impact on such kind of jets, especially forming these vortices and so on and so forth. So we all know that the typical AGN spectra tends to have these two hump structures. If you look at the continuum spectra, where the low energy hump is mainly dominated by the synchrotron emission and the high energy is dominated by the inverse Compton processes or the hadronic processes. But the question still remains that what is the particle components of the jet, and what is the physical reason for such high energy emission, and whether it is unique or it's a universal for all the AGN jets. Probably not true, but there have been studies to understand such kind of features. And what we want to understand, another aspect, is as far as the polarization is concerned, because that also gives a very important clue on the structure of the magnetic field, especially at very large scale, and how that can be related to what is happening as far as the emission signatures are concerned. So with this in mind, what we do is, again, we adopt this idea of focusing at much larger scales, and we focus on a small portion of the jet. Now, treating it not relativistically, because we're treating now at a much higher scale, that is kilo-parsec scale. And what we do is that we incorporate certain magnetic field profiles, axial magnetic fields and helical magnetic field profiles into these kind of structures, and try to see what are the impacts of these magnetic field configurations on such kind of plasma columns at much larger scales, and then understand that once you have such instabilities being developed, how do these instabilities then characterize the non-thermal emission process? So here are a couple of movies that I would like to show. So here you basically, on the left-hand side, you can see the evolution of a plasma column. This is the density for the case where we have axial magnetic fields, meaning all the magnetic fields are along the plasma column. And you can see how the plasma columns become highly turbulent in nature, and this basically all the flow is going along the magnetic fields. And because of this shear that is existing between the the jet and the ambient medium, you generate these Kelvin-Helmholtz vortices, and you make your jet extremely turbulent and with shear. But if you now add the toroidal component of the magnetic field, the evolution on the right-hand side is slightly different, where you basically do not see development of such Kelvin-Helmholtz vortices, because the toroidal component of the magnetic field acts like this pressure barrier, which does not allow these vortices to actually develop and saturate. And therefore, you have much more steady kind of behavior of such kind of jets, not rather very turbulent, as you would see for a typical KH-dominated disk structures. So just to give you a highlight, if you have a KH-dominated, which is axial magnetic field, you have much more turbulent structures, and lower sonic numbers would have much more turbulent structures. But if you go to with the toroidal component of the magnetic field and higher sonic Mach numbers, that is fairly more stable because of the magnetic field effects. So the important point again now here is that, okay, if we have these kind of structures, how do we go about understanding the emission mechanism into this? And for this purpose, we don't do multi-zone processing, but we do a slightly more better approach, which is a hybrid macro particle approach that we have developed for the Pluto code. And here the idea is that you basically incorporate, what you do is in a 3D simulation, inject particles that are moving along with the fluid, and as they are moving along with the fluid, they actually track the local conditions of the magnetic fields and shocks and so on and so forth. And based on that local conditions, they evolve their particular spectra. And then once the spectra is evolved, what you can do is you convolve with the synchrotron spectra to basically get the complete emission mass. So with this kind of approach, what we have shown here is the structure of this particular plasma column, looking very at a very top really on the top of the jet. There you can see such kind of features, eight-like features that are very common for a KH unstable jet, where you have this interface getting unstable, and you produce such kind of jet there. You produce such kind of features over there. And we have shown here that for different frequencies, and as expected, as you go to higher and higher frequency, the amount of emission keeps on reducing because of the strong magnetic fields. Because of the magnetic fields, you tend to cool down these processes. So the idea was that now, if you, yes.
5 minutes more.
Yeah, I'll just wrap up in 5 moments. So the thing is, if you go to slightly more, the idea is that if you look at now with shock hands, with shocks, what you see basically is that these particles tend to have, here I've shown basically the normalized flux. You can compute the normalized flux for each different region, and then you can plot the SEDs for different frequencies. So here is basically the frequency on the x-axis and the normalized flux and some scale on the y-axis. But what is interesting is that this is a time evolution. You start with a much more steeper flux, and what you see is that this spectra evolves in the synchrotron band, and what you have is a spectral hardening of spectra, mainly in the X-ray band. And that is mainly because of the particles getting accelerated due to shocks, as we will see. And such kind of features are also seen if you take into account the inverse Compton emission. And then if you look at the amount of emission that is coming out, or in the band in which such emission due to spectral hardening will come, it's mainly in the TV band. And these jets tend to have emission in TV band. So basically, to understand slightly in more details, what we have shown here is basically in the background, the pressure distribution in the orange color, and the synchrotron emission in the X-ray band is overlaid on top of it. So these are contours of the synchrotron emission process. And what is happening is that this energy, or the particles which are getting accelerated in these shocks because of the KH instabilities, are getting accelerated again. You get these secondary electrons, and you have these transient X-ray events which are responsible for these spectral hardening, which are transient features, and then they again cool down because they are not getting pumped up due to shock. So such kind of instabilities are extremely crucial to give rise to such transient features in our SED distributions as well. So again, this is another recent work by Dipanjan, who is a collaborator of our group here. And he has also demonstrated such kind of features not only in the particular plasma column, but even in larger scale jets, where you can basically see that there are these regions of these particles where the shocks are getting, where the particles are getting activated due to shocks. And these are the number of shocks, because there are multiple shocks that are being acting as you basically move along the jet. So the particles are getting re-energized due to these shocks, especially in kilo-parsec scale, as you go along and getting energized and getting accelerated, giving rise to X-ray emissions in the X-ray band. And this can be an interesting application or interesting understanding if you want to really understand these bright features, which is associated with these PKS source, where they have seen that is observed X-ray synchrotron, and if you basically get the X-ray flux and if you fit it with ICCMB, then you really need very, very highly relativistic jets, which is definitely not the case, and definitely doesn't agree with the Fermi, upper limit of the Fermi flux. So the only way to explain such kind of thing is secondary synchrotron processes, which is what we also propose as a probable mechanism, especially when you have such turbulent KH instabilities acting in such kind of jets. So what lies ahead? Just a couple more minutes. This is definitely just a tip of an iceberg which I have explored here with numerical simulations. But there are, of course, we have young students here, and what lies ahead is that there are exciting time to do black hole physics and jet physics. Because if you look at the EHT that is coming up, there is a lot of things that is basically still yet to be explored. And very recent results, which was published in Nature, we showed really this structure, the hollow light structure in Centaurus A. And you have also this zooming in effect of this light coming from the black hole. And EHT will definitely show us some path ahead, understanding what is really happening very close to the black hole. And another interesting aspect which is now being explored is high energy X-ray polarization. And this would be an important understanding from the perspective of the magnetic field, especially at high energy aspects, especially responsible for such instabilities and so on, to understand what is happening at the high energy. And if you look at the very low energy or the low frequency, the upcoming LOFAR, MW, and SKA would give rise to a slew of AGN jets with extremely different features, rich features, which will be, of course, a challenge for theoreticians and numerical simulators to actually explain such kind of features and how do they come about. So with this, I would like to summarize that astrophysical jets indeed has a history of 100 years, but there are several important questions still yet to be answered. And mainly because of the complex nature of instabilities and features that are existing, it becomes much more complex and one needs to handle them from numerical simulation perspective. The community is going in a direction of simulations, doing hybrid simulations, understanding from the multi-scale physics perspective, at a very micro scale using the particle in cell simulation, which I have not discussed in details, but there are also hybrid simulations explaining emission at much larger scale. We have shown GRMSD simulations have also progressed, and we have demonstrated production of Blanford pane wind for the first time. Of course, in study of instabilities is an important aspect, and we have also shown how kink instabilities can give rise to long-term variability signatures. And finally, what we have done at the larger scale is that we have given an explanation, a possible explanation of generating secondary electrons to explain X-ray components in PKSOs. I would end now. Thank you so much for your time and attention.
Thanks, Bhargav, for taking us to a nice tour of AGN Jet. So now we will have time for question and answer. So please raise your hands or post your question on the chat box. So I see already some hands are there. So Indranil, please go ahead and ask the question.
Hi, Bhargav.
Hi, Indranil. How are you?
Fine. You spoke as fast as your jets are. So you put so many matter. I have about 10 questions. I can't ask them all. all of them.
You can ask them. That's it.
Later on, maybe, yeah. So I will just I'll just focus on one or two questions. One is that the busy jet is essentially in the MD regime, right? Not in exactly in the MHD regime.
Yeah.
Okay, and also the BP winds model for the winds, they also are notoriously, they don't depend on accretion states. While we see that jets are in the, I mean, they're typically related with the accretion states. What is your take on that? That's the first question. There are many questions.
Can I answer this first?
Okay, you can answer this. I can ask the next question.
Yeah,
later.
yeah. I think you really hit the nail on the coffin. So basically, the thing is that when you do these GRMAG simulations, one of the biggest issue or in the community from numerical simulations perspective is to really understand what really happens pretty close to the black hole. As far as the numerics is concerned, still it's still what we call is like what you can say the floor value in technical terms. So essentially what you do is very difficult to handle numerically. I'm answering from technical perspective, then I'll answer from the physical perspective. Numerically, in that particular region, very, very close where you have the ergosphere and so on, you have extremely high value of sigma. And this becomes extremely difficult and what you can say a hard equation to solve from the relativistic MHD perspective. And so what we do is we basically put some sort of a floor value so that the density or the pressure doesn't go beyond that particular floor. And indeed, these Blanford-Snack jets to belong with actually is this floor value pressure. Okay, but the point here is that even though you are talking about floor value, what is important and what I understand is important is how your matter is, how your magnetic flux is basically getting accumulated. That is a very crucial ingredient. Right. And the way the magnetic flux is distributed within the disk determines how your jets are basically getting coming up or shaping up. So for example, if you do not, so for example, in our simulations, when we start with a much vertical field, we never see Blanford plane wind, never. We only see because vertical magnetic fields, they get curl on and they produce toroidal component, and you always have these tower jets to begin with and turbulent structures. So we definitely need much more inclined magnetic fields. Now the question is, how do these fields come about? There's a different question altogether. True. Right. So that is another thing. So agreed that accretion states may not guarantee this. What is crucial is the magnetic flux distribution within these particular accretion districts. That is a much more crucial ingredient. Okay. And indeed, you are absolutely right. Blanford-Snack jet is an MD mechanism. The GRMAG are not evolved to that state to really do that kind of things right now.
Okay. Next question is the magnetic field structures. I mean, near the black hole, because we know that the magnetic field is not supposed to enter, right? While you are having your simulations are showing, reconnections galore. So do you have, I mean, are you sort of, is it first of all, is it a resistive code or, resistive MHD code, or you are, by hand putting the resistivity?
Good.
While we know that resistive codes are very difficult to handle.
Yeah. So it's a very good question again. So this simulations have been done with ideal GRMHD code. So as you are aware that each simulations or numerical simulations have grid-based resistivity.
Right.
So with this, I would say that indeed, whatever reconnection that we see is mainly due to the resolution effect. However, these are adaptive mesh refinements. Even with resistive GRMHD codes, they have seen such kind of features. So
I spoke with Shinji. I spoke with Shinji, and Shinji showed his simulations, resistive MHD simulations.
Yeah.
But Shinji Koide's code, the numerical scheme was very old.
Yeah.
So I myself did
this
not trust much.
This is by Bhargav. This is black hole accretion code. Okay. They also have a public version of resistive GRMHD now available, so one can do. But there have been groups by the in US, the Flatiron Institute groups, they have actually been doing this, and they do see, even in ideal and non-ideal, they do see such kind of reconnections happening, even in 3D.
Okay. I have stopped now because I think there are many people who will be asking questions.
Okay,
so
sure.
we should have.
Sure. Thanks.
So, Samrat, please unmute yourself and ask the question.
Hi, can you hear me?
Yes, I can. Yes.
Yeah. So this is Pankaj here. Sorry. So I will go into practical aspects. So Bhargav, very nice talk and overview. So the thing which I want to know is, like, you showed this kink instability light curve, synthetic light curve that you generated. Now you have a periodicity there, but in general, AGN variability is stochastic. So how do you see that one? The second thing is, okay. So there is another, the other connected part is, like, you have showed, so you have a kink instability where you have, I can see if I see the regions, there are 3, 4 that kink places, right? And you have calculated from 1, but if I guess from the figure, all 4 seems more or less equally prominent in emission. So how do you reconcile these 2 facts?
Okay. So basically, this work, I must tell you, this was mainly as a proof of concept to understand, because you see, these geometric models which have been proposed, they never are demonstrated using numerical simulations, as far as what is the time scales are concerned, what are the magnetic fields that are in there. And the main motivation behind such kind of work was to show a proof of concept that kink instabilities can produce variabilities within that particular time. So indeed, this is a toy model. You are absolutely right that as a periodic condition is definitely not something what you see, but there has been also recent work by a group in Purdue with Dong et al. In 2020, if you know this paper. They also have shown the existence of kinks and how this kink can affect such variability signatures, regular variability signatures. Now, of course, by the construction of this model, you will get the periodic signatures that you have. But if you look at the overall jet structure, okay, you do not see such kind of periodicity. And that is mainly because of the fact that you are actually catering to a different sections of the jets while you are doing the line of sight integration. And indeed, when you said that the different kinks that you have, yes, this is something which we input. This n equal to 4 is like a perturbation that we input just to demonstrate that what is really happening. And we focus on one particular region, and I can bet that if I look at the other region as well, it will be the same profile, because this is exactly the thing. But the important point here to highlight was that we are seeing structures which are actually coming to your line of sight and getting more enhanced in relativistically beamed. And that is what the intention was to demonstrate over here, just to demonstrate a proof of concept of such long-term variability. If you really want to understand the important aspects and really want to do a 1:1, first 1:1 is very difficult. Statistically, one has to compare. But if you really want to do, you need to do a slightly more large scale jets where you can produce the kink. But the problem is that there you can produce kink, but you cannot track kink at a very long time. So you will have to go away with such kind of compromise. So that is what I would say.
Okay. Can I ask a few more questions, or
one more, and then later probably end of the.
Okay. So the other question is related to the simulation where you showed that you have a setup where you have a thin accretion disk, and then you launch this BP flow and the jet, right? So, and then you are talking about MAD. What I am confused is, like, so this thin disk is actually Sakurai-Shinya type disk?
Yes. Yeah. So basically, this thin disk is initialized to be a Novikov-Thorne disk. So Novikov-Thorne disk is, in a way, you can say that it is more like a GR potential stabilized disk. Okay, it is definitely moving almost at Keplerian speed. And the reason why we say MAD is because what happens is that we don't initially start with MAD configuration. So there is, so what we do is we physically initialize with a stable disk. Okay, so this is like an initial condition. And then when we incorporate these magnetic fields, what happens is that in these simulations, the resolution is such high that you actually resolve the MRI scale, the magneto-rotation instability scale. And once you do such kind of resolution, what happens is you start to accrete matter because of the loss of angular momentum. And along with that matter getting accreted, you also accrete the magnetic flux. And the moment the magnetic flux exceeds certain limit, and we have estimated this, I don't see the plot here of magnetic flux, but if you exceed certain limit, it is basically regarded as MAD. And if you look at this black curve, see, if you in the initial part there is no oscillation as such, but after a certain time, it starts to oscillate, and this is where it actually crosses the MAD limit. And what happens is that you actually accumulate the magnetic flux, and the magnetic flux kind of acts like a barrier, and you cannot penetrate that, and therefore this will basically go back, and then once again it will come back in, and so on and so forth. So it is reaching a MAD state. Okay, it's reaching a MAD state. We don't start with a MAD disk. It reaches a MAD state, and all those MAD disks are prone to oscillations. That's what we see.
Yeah, so what common feature I also see here is, again, there seems to be a repeating pattern either in the jet or something. So the thing which I like from
but the repeating pattern is kind of different in kind of like, there is a repeating pattern, but the period is slightly different.
No. So I am not going directly into the observation. What I wanted to know is, this seems to be a generic feature. If you set up such a jet, and you will always have this, whether the time duration between two peaks is different or something, but this is a generic feature, right?
Yes. See, basically, this is a very generic feature when you have started to do 2D simulations. Now, people who are doing 3D simulation, there is an interesting feature. Now, when you do 3D simulations, you are essentially dealing with the flux tube. Okay, so this is not just 2D plane, but flux tube. Now, what happens is that if you keep on, so for example, here I will show you. So this is a flux tube in 3D simulations. Now, if you manage to keep this flux tube intact for a longer time, then this acts as a barrier, and you will always have oscillations. But if you basically shear out this particular flux tube on a much shorter time scale, then you may have much more reduced oscillations. But these oscillations are present at some level or the other, and they can be transiently generated based on the generation of the magnetic flux. That is the point.
Yeah, thank you.
So Ritaban, could you please unmute and ask the question?
Yes, thank you. Bhargav, can you hear me?
Yes, Ritaban, hi, how are you?
Hi, good. Nice talk. So I had a very quick question. So at some point you said that in the large scale jet, you are assuming non-relativistic. So I was just wondering, what does relativistic or non-relativistic mean in the context of your simulation? And is there an observational reason to assume that it will be non-relativistic in the large scale?
Yeah. Okay. So I think it's a very good point. As far as the simulation is concerned, it's mainly the physics, the set of equations that we solve. For the RMHD, we solve the set of relativistic MHD equations. For non-relativistic MHD equations. And the idea behind adopting such an approach over here, at least in the kilo-parsec scale. So what we do is typically when you go to kilo-parsec scales, there have been indications that the Lorentz factor reaches up to about 1.2 or 1.1 in typical length scales, because we are focusing on one particular region though. So instead of basically doing the much more relativistic environment, we basically adopted the non-relativistic equation to solve the set of equations. However, even if you adopt a relativistic equation, the features will not change because the game is played by the magnetic fields. Okay, irrespective of the dynamics, the relativistic or non-relativistic, the game is played by magnetic fields, and that is an important point here. That the magnetic fields kind of govern the stability part, and it is irrespective of what you basically have as a kind of relativistic or non-relativistic. So that will not affect much as far as the emission signatures are particularly concerned. And the main intention or the main approximation was that at such case, you basically become gamma close to 1.1, 1.2, and therefore you can treat it like almost gamma 1. So it almost becomes gamma 1.1 because of the
Okay, thank you. Thank you.
Raj, please go ahead.
Hello. Yeah, sir, can you hear me?
Yes.
Yes.
Yeah, so I have a very quick question. So regarding the 2D simulation you showed, there were winds and jets originating, right? So, but generally, observationally, it is seen that these two exist on a very different accretion state. So, like wind is on high soft state, while jet is on low hard state, where wind disappears. So here, which accretion state you are taking, where like these two are appearing?
Yeah. So it's a good question, Raj. Now, actually, the whole point is about time scale. Okay. So when you take about hard state, soft state, this transition of hard state to soft state, it's a huge amount of considerable time. Now, these GRMAG simulations are highly computationally expensive. So if you look at and see, the thing is everything is scalable. Okay. So here M is a scaling parameter. M. It's a mass of the central
Mass of the black hole. Yeah.
or mass of this compact object. Now that is a scaling parameter. Now, based on the choice of your M, you either are doing the simulations for few seconds, or you are doing the simulations for few years.
Yeah.
Okay. Now, when you are doing this, we have actually understood this where this is. So what we see is that this feature, because we have this transient jet-like feature, this is mostly in this transition phase from hard to this state. So this is like intermediate state, but we are not even capturing the whole transition also. It's mostly somewhere in this intermediate state.
Okay. 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 Fine.
Shamik, if you have a question, please go ahead.
Hello, am I audible?
Yeah.
Yes.
Okay. Hello, sir. So I have a question related to the simulation. Like we already know in literatures that people are doing simulation vastly with the thick disk model, right? And in your simulation, you have started with the Novikov-Thorne thin disk model, right? So other than this Blandford Payne wind, is there any new features that you can say, or is there any advantage of taking thin disk model over the thick disk?
Yeah, that's a very good question, actually, Shamik. See, the thing is that people have been using there are advantages of disadvantages and advantages both of such kind of things. As far as the advantage of this torus-like simulation or thick disk simulation is concerned, you self-generate the magnetic fields as such and see how the structure of magnetic fields evolves. Whereas in the thin disk, you have to impose the magnetic field structure. That is an interesting, important aspect there. But only when we could impose such kind of magnetic fields, we could see the evolution of the Blandford Payne wind. As I said, that the inclination was an important aspect. So along with that, you can also see features whether the disk kind of survives or not. Though we are not having a constant injection of material from the outer part, but you can at least understand what is the feature of the disk and the formation of the corona in such kind of structures. So these kind of features we can very well study from such thin disk environment rather than the torus. So torus is basically more sort of what you can say much more consistent, but much more simplistic. That's what I would say. Thin disk is rather more kind of more tricky to give, but of course it has its own pros and cons. But you can now relate the accretion rate, or at least study the disk-jet connection with such kind of thin disk models. That is an important aspect which you can capture.
So can I ask one quick question? Like, so since you want to study the jet behavior, so your system has to be turbulent in nature, right? So since you are using the numerical simulations, so we know that in numerical simulation, if you start it, if you evolve it for a long time, there should be some kind of numerical turbulence or numerical resistivity. It will automatically develop. So does those effect are negligible, or it does not affect? Is it negligible or something like that?
Basically, see, these kind of things do initiate some perturbations in your flow, but the point is that the physics is basically governed by the perturbation growth, and that this resistivity can induce perturbations, but this perturbation growth is governed by the physics over there. So that really do not hamper much, but to do more qualitative and qualitatively, definitely it doesn't have any effect. Definitely.
Okay, sir. Thank you.
Okay, so there are two questions in the chat box. So if you want to take that, Okay, so yeah. Do you want to read it, or I can read it?
Does the Milky Way galaxy ever had AGN? If yes, what effect did it have on the evolution of the Milky Way? Yes, well, there have been indications that there are some jets very low flows, but could be. I mean, that's something which. And what effect does it have on the evolution of Milky Way? Well, like all galaxies, AGN jets do affect the parent galaxy. So probably during the early time when Milky Way was probably throwing a jet, it would have been much more active in that particular space. And yeah, I mean, that is what I can say. And not in these areas speed higher than light speed like 6 times. That is essentially an aberration effect. It's mainly an aberration that is something to do with the light travel time effects and observational aberration. So this is something very textbook aberration.
And there's one question on the top, Jaydeep, why the
parameter process is important in 1D model? Are these processes subject scale or some interaction terms which are not explained? 1D, one zone. No, the thing is that in one zone you do a steady state approach. So basically you have a blob in one particular environment, the magnetic field and so on, and then you basically can throw all sorts of physical parameters to it and understand and fit the SED spectrum. So they are not subgrid, they are subgrid scale physics, but they are related to not changing. So they're like steady state. So one can do all sorts of complex subgrid physics in steady state approach. That's what I can say.
Okay, so Dipankar, could you please unmute and go ahead? Yeah.
Finally, Dipankar.
Hi, Bhargav. Thank you very much for this lovely talk. As you can imagine that you can see that many more questions are waiting. So I hope you'll be able to visit us sometime, and it will be really very nice to host you here. So thank you very much. I have one question, my limited knowledge on the subject. Of course, this I was just trying to see that your KH instability grows slightly faster. And then it appears that the kink is, providing a sort of, halt to that, as you mentioned, the toroidal field suppresses the turbulence growth and all that. So how do you manage these things in terms of your time scales of simulation? So that's part of a simulation question. The other thing is in terms of observables. So are these things, possible to be observed by, radio imaging and things like that? Because we are more familiar with seeing, radio snapshots where you do see, certain features which does show you the presence of turbulence. But whether, a time evolution of such things are possible now, because I'm not familiar with the subject. I
think it is a very, very interesting and important question. And the important aspect behind this, the growth of these instabilities is mainly governed by the alphanic Mach number. Okay, so how basically you are super alphanic or subalphanic. And this is basically governing whether you are actually, and also the fact that if I have an actual magnetic field, as far as the simulation is concerned, even though I have magnetic field, essentially I'm doing an hydro simulation because the flow is actually going along the magnetic field and there is no hindrance for the flow. Okay, and then basically it's all governed by the subsonic or either subsonic or supersonic, and then you generate this KH instability. As far as the competition between KH and kink is concerned, the main governing factor is basically the strength of the toroidal component of the magnetic field, and that governs the time scale. Now, and that basically tells you how quickly it can saturate such growth of KH instabilities and make it much more stable. And as you can see here, so basically when I go with a much more supersonic case, with the same magnetic field strength, I'm not basically getting much more turbulent features because it's kind of getting killed right from the beginning as such. Now, how do these translate all into observation is more sort of an indirect way. And that is what we are kind of hinting, that such KH unstable jets tend to have signatures, very distinct signatures in this SED, that is the continuum emission that you get from these jets, covering all bands. So mainly this is X-ray band here, which I'm focusing on. And the idea is that if you have strong kth instable features in your thing, you tend to produce strong shocks because your kth instability is not saturated. You produce strong shocks. These shocks accelerate particles to high energy, and you generate X-ray emission, transient X-ray emission. And this transient X-ray emission gives this kind of blip, or the spectral hardening, that is what we call in the continuum emission. And these blips are always observed in several features, in several AGN Jet SED signatures. And this is extremely crucial. And one can explain such kind of transient features based on such instabilities. Additional insights we will get mainly from high energy polarization, because when you see high energy polarization, we will be able to now directly see how these magnetic field features are happening at these highly energetic emission regions. And if you believe that these shocks, then you must have some more structured magnetic field configurations. And therefore, clues from observations will be rather more indirect, and one has to do an interpretation in some sense. But one can do such kind of bridging now with numerical simulations to provide some interpretation for.
Thank you. Thank you. Very nice. Yeah.
Yeah. So since we are already late, so Bhargav, can I ask a quick question? So what is the typical time scale of this disk detaching in your simulation that you showed that disk is detaching? So what is the typical time scale of this?
Yeah. So basically, as I said, the time scale governs by the mass. So if I take an X-ray binary, so for example, a stellar mass black hole, I think it's of the order of few seconds. No, not few seconds, few milliseconds. So the whole simulation is few seconds. Okay. If I take the black hole mass to be a stellar mass black hole, then the whole simulation is about few seconds, and this will be about few milliseconds. I think.
Okay.
Shubhendu,
yeah.
Just one clarification. Bhargav, in your simulation, did you find any fast winds?
Yes. These are fast winds in the sense. Okay.
It's crossing the fast magnetosonic point.
Yes. Of course. Yes.
Okay.
This basically, you see, this is the alphanic Mach number. Okay. This is black line is alphanic Mach number, and then basically also have a fast Mach number somewhere up there. So these are super fast. So
super fast. Okay.
Yeah.
Fine.
Okay, so we can close now. So thanks, Bhargav, again, and
thank you so much.
We have to have you here at Aries sometime in maybe near future, and we discuss more. As you said, as you may found that we have many questions and many comments. So okay, so I thank all the participants for attending the seminar. So with this, we close for today, and we'll meet next week again with another talk. So take care and bye-bye. And
thank you so much.